All right, so today we're going to be going over section 14.4, which is a change in concentration over time. So just to review, we're going to look at our rate law, which shows how rate depends on concentration. Right here, we know all of this. We know our rate constant. We know our concentrations to their respective orders. We understand all of that. Today, we're going to be looking more at integrated rate law, which is used to calculate the concentration of a reactant at a specific time, given the initial concentration and the rate constant. We're just adding more variables, and it gives it a y equals mx plus b format, which is of a graph. So we're going to be using that again now to determine the rate law from graphs. So linear graphs are used to find your rate laws. You don't need to understand zero, first, and second right now. I'm going to go into that in just a minute. But what you need to understand from this slide is that your slope is your rate constant. Your slope here, it's a negative slope. It's your negative rate constant. Here, slope, negative rate constant. And once again, here, your slope is your rate constant. Now, most people know how to solve slope. Obviously, it's y2 minus y1 over x2 minus x1. Putting it into the context of the problem, though, we have this. We take our point here, and we put it minus this point here. And that is going to give us a slope of 0.54. And obviously, like I just said, our slope is equal to our rate constant. So that is also going to be our K. Perfect. So now we're going to look into what I just talked about, the orders. Now you looked a little bit about the orders and rate laws, and this is how we're going to understand them from a graph. So when you're plotting something, you're going to plot concentration and time. Time on your x, concentration on your y. Now, it's pretty simple here if you have a zeroth order equation. If you plot these two things and it's a linear, then you know it's zeroth order. There is no change. The rate constant is not dependent on any concentration, which means it would be something like this. It would be, if you had a rate law like this, it would be a to the 0 and b to the 0. Then your rate is just your rate constant. There's no dependence on your concentration. So this is going to give you an integrated rate law in the form of y equals mx plus b, like I just showed, of concentration of A is equal to negative rate constant times time plus the concentration at 0.0. So it just helps you understand it in a graph if you put it in the integrated rate law. So that's zeroth order. Next, we're going to look into first order. Now you notice the units here are a little bit different. This is natural log of concentration and then time. So here, obviously, first order is going to have a 1 right there, which we don't need to put, but it's your rate constant times your concentration, which means it is dependent on the concentration. So your integrated rate law, again, is just going to be changing this to ln. So why it is that the units are different is explained in a matter of derivatives. Now, if you've already taken calculus, you understand how derivatives work, but for the people that haven't, a derivative is the instantaneous rate of change, which basically means a rate at a specific point in time. If you click on a specific point, it's going to have a different rate unless it's linear, right? So to make everything simpler, we want to get it linear. So when you have a first order equation, since it's dependent on the concentration, when you plot concentration and time, it doesn't yield a linear graph. It yields something like that, right? And that's not what you want. So in order to get it to be linear, you have to derive it once. The derivative of that concentration is the natural log of concentration. Natural log of concentration over time, that's going to give you a linear graph. If you derive it once from here and it turns linear, that's how you know it's a first order equation. And that's something you're going to need to know. But also, it remains constant that your slope is k. So taking that a little bit further, if you want to go and if you take something like this and derive it once, but it turns out like this and it's still not linear, you have to then derive it again, which the derivative of ln of something is 1 over something. You don't need to understand why it's that per se, you just need to understand for now that it is. But basically, the amount of derivatives needed to become a linear graph is going to tell you your order of your reaction. So for example, it'll give you a graph like this and you'll derive it once. And if it gives you this, you know, okay, first order, that's the correct answer. If you derive it and then it gives you that, then you derive it again and it gives you that, you know, okay, third order. And like I said, your y is going to change as you derive it. Derivative there, first, derivative there, second, derivative there, third. We only go through 0, first, and second, but I put the third there just for the theme and just to understand the process. You're just going to keep deriving, okay? So That's how you find your order from a graph. You're going to derive it until it becomes linear. And the amount of times you have to derive it tells you your order. It's that simple. So, like I just said, this is going to give you your second order, right? You have the 2 times the concentration, and it's just going to give you a new integrated rate law. Now, these rate laws, you are only changing 2 variables, so it's pretty simple, but they're going to help you with the practice problems. The first order rate constant for the decomposition of N2O5, the equation is 2 N2O5 gaseous yields 4 NO2 gaseous plus O2 gaseous. At 70 Celsius is 6.82 times 10 to the negative 3 seconds to the negative 1. Suppose we start with 0.0250 moles of N2O5 gaseous in a volume of 2.0 liters. So our question is, what is the concentration of N2O5 after 5 minutes? So we're looking right here for a concentration at time t, which is 5 minutes. We know that it's first order, so we're going to take our first order equation from earlier and plant that right there. We know that's what we're going to be using. Additionally, we know that this is our rate constant, so we can plug that in our variables right there. So starting with 0.0250 moles in a volume of 2.0. That's essentially telling us our concentration here, but we need to get it into something we can use. So we're going to use molarity, which is moles divided by liters, to get 0.0125 molarity. Okay, so we know that that is our concentration at time 0. Again, we need to put our time, 5 minutes, into something we can use. Time is usually in seconds, so we need to convert that. 300 seconds, easy. Now is when we start to plug in stuff to our original equation here. So we know that it's decomposition, so that's all that's saying. It's negative decomposition. We don't need to put the negative in there. It's just telling us that it's decomposition. So we plug in our K, our T, and our concentration at time 0. Negative 6.679 is the natural log of our concentration at time t. But we're looking for our concentration at time t. So in order to undo our natural log, like I said before, the opposite of a log is an exponential. And e to that number is going to give us 1.3 times 10 to the negative 3 moles, which means that at our concentration at time of 300 seconds is 1.3 times 10 to the negative 3 moles. And that's the process. If you understand how to do that problem, great. If you don't, rewind, watch through, work through it again. This is how most of the problems are going to be set up. You're going to be solving for something. Whether it be 0th order or 2nd order, you're going to use the equation for that respective order and just solve through it. Perfect. One more thing we have to go over is half-lives. So a half-life obviously is the time it takes for a concentration to drop by 1/2 of its initial value. For first order, the equation is going to be 0.693 over our rate constant. You don't need to understand why it's 0.693. It just needs to be something that's memorized. For our second order, it's going to be 1 over K, our rate constant, times the concentration at time 0. You just need to understand that those equations are what they are. But it makes the problems pretty easy. So we're just going to go ahead and do this quick problem. What is the half-life of N2O5? So we knew previously that it was a first order, so we're going to go ahead and use this equation, the first order equation. And we remember our rate constant from before, so we're going to put that in our variables. Now, this is a pretty easy problem, and this is really a pretty easy concept because you just use the equation and plug in your variables. So we're going to go ahead and plug that in under, and it's going to give us a half-life of 101.6 seconds. And that's all it is to it. That is a quick overview of chapter 14.4, and I hope that helped, and have a nice day.